Okay, now, when we finish instruction in the different gas laws, you're going to be expected to figure out which gas law you have to use. I'm going to start out with one gas law and give you a problem, and another gas law and give you a problem. So initially, when we're setting this up, you're going to know which gas law to use anyway. But if you don't follow the steps, you won't have the tools you need to choose the right gas law. And on the test, and later in the unit, you're going to have to pick the correct gas law. I won't give it to you. Okay? So that's what this problem-solving series of steps is all about. Shane, since you're kind of back there, would you just go around and turn off those stir stations, please?
Thank you.
You can turn them all off. Yeah, just you have to turn the knob until the green light goes off. You got it? And there's one behind you too. Yep. That's it. All right. So let me give you a problem of the type that you might see on a test. Okay? Okay, so here's our list of knowns and unknowns. Let's go through the problem with me. Please follow along closely. Read the problem with me. Let's together interpret this problem. If Dick has a cylinder filled with 4.7 liters of methane, that's a known amount. Well, liters measures what dimension of measurement? Volume. So this is a volume. Okay? Well, it might be V1. Let's just list them in the order we get them first and see, okay? So we know that one of the V's, if there is more than one, is going to be 4.75 liters. Okay? That's a known. Okay? At a temperature, well, it tells you its temperature. I could have just said 35 degrees C. You should have known its temperature. But I wrote temperature here. So we know that's a temperature of 35.0 degrees C. Okay, and the temperature has changed, got a new temperature. That means this must be temperature 1, and the new temperature will be temperature 2. And it's decreased to, it says, temperature 15 degrees C, 15.0 degrees C. And then it asks you, what would the volume become? So we have a new volume here at this new temperature. That'd be V2. Yeah, so that must be V1 up there. So we don't know what that is. We're going to put a question mark there, just for now. Okay? All right. So now we go to our list of equations, our gas laws, and the one that fits this list of knowns and unknowns is this one right here, where we have V1 and V2, and T1 and T2.
Oh, okay.
See that? So choosing the equation once you make your list of knowns and unknowns should be easy. So let's write down what we have there. V1 over T1 equals V2 over T2. Now we have a problem because, and this is something you just have to know, you cannot solve gas law problems with the temperature in degrees C. Said that yesterday, and you have to know that. You have to change the degrees C temperatures to Kelvin temperatures. Okay? What? There you go. Guess what? It's there in your test references right there. All right? So we need to take this 35 degrees C, 35.0 degrees C. If we're going to change from degrees C to Kelvin, we add 273.15. 273. You putting $1 or something in there? You need to put. You have to have $1 in there or something equivalent. Okay. 273.15. That's what we're going to add to that to get the Kelvin temperature. Yes. Yeah, do that for both the temperatures, yes. Okay, so we got 35 plus 273.15. Oh, got to turn it on. It helps when I do. 35.0 plus 273.15. I get 308.15. Okay? And that's going to be a Kelvin temperature. Please pay attention. But we have an empty slot right here. Uh-huh. If you're converting from degrees C to Kelvin, you add 273.15. If you're going the other way, you have to subtract. Wait a minute. I'm sorry, I can't hear you. We want to ask people around you to be quiet so I can hear you. Thank you. Go ahead, Sierra.
Do we always add the same number?
If you're converting from degree C to Kelvin, you're always adding this number. That number will never change. That's right. Now, if you're going from K or Kelvin to degree C, on the other hand, you have to subtract that number, but the number stays the same. Okay? All right, so we have a digit here that's going to be insignificant. So we're going to round this number then. It's not a focus, it's the contrast. Okay? Our temperature is going to be 308 point. Nope. 2. The 5 makes the 1 round up to a 2. Okay. All right? So this temperature over here then becomes 308.2 K. All right? But we still have to change this one. This one also has to be changed. All right? So that's 15 degrees C. And we add 273.15 to that. All right. We have to convert this to Kelvin as well. We can't use any temperatures in degrees C for gas law problems. So we've got an empty slot right here. Okay. Going to underline, round off. And that's 288.2 K. So this is 288.2 K.
I thought you had a 2 and a 1, but it's the K. The K right here.
Okay. All right. So now we're ready to plug in our known values in this equation. Okay, here's our gas law equation, and we're going to plug in our known values into this equation. Okay? All right, so we know what V1 is. It's 4.75 liters. We now know what T1 is in the correct units of measurement. That's 308.2 K. So T1 here goes 301.2 K. We write an equal sign. We don't know what V2 is, so we're only substituting in the equation only the known values. Okay, so V2 is going to stay V2 because we don't know what that value is. Yeah. Not really. It wouldn't hurt if you did. But see, the species doesn't change here, so we don't need to put methane in the equation. Does that make sense? It's when the species is changing that we have to make sure we always have our species in there. Like what? Like in stoichiometry, correct. Okay? All right, so we do know what T2 is. We found out that it's 288.2 K. So we're going to plug that in for T2. Okay, so that's that step. That's the step where we substitute the known values in the equation. Substitute the known values from the list into the equation. That's what we've done here. Okay? All right. The next step in the problem-solving system that I gave you was to isolate your unknown. Isolate your unknown. Well, your unknown is V2. We're not going to do cross, multiply, and divide. Is everybody listening? Because this is really important. I have a lot of students that try to do it. Guess what happens to their test? Okay? Cross, multiply, and divide will not work for a lot of our gas law problems. If you try to use it, the chances are really high you're going to mess up. Okay? So you are not allowed to use cross, multiply, and divide here. You understand?
Okay, so what do you do?
Not allowed. All right, here's how we're going to isolate the unknown. In order to get isolating the unknown, what we're trying to do is to get V2 all by its lonely little self on one side of the equalities, the equal sign. Okay? Now, what you have to remember is whatever you do to one side of the equation, you have to do to the other, so it stays equal. And the way we're going to do that is we're going to multiply both sides by something that's going to get rid of this 288.2k. 288.2k goes on in a fraction over 1, and that is going to cancel this whole 288.2k. You remember that from algebra? But if we do it to this side, if you do it to this side, you also have to do it to this side. 288.2k over 1. So I'm going to do it to both sides. Okay? Alright. Now we're going to do the same thing we've been doing since the very beginning of this class. We're going to cancel units. Got k on the top and k on the bottom. They can cancel out. And look, here's the nice thing about this sort of setup. It's called dimensional analysis for a reason. The units of measurement we have left are liters, and liters measure the dimension of volume. So we know we probably got the problem set. We have a really good chance we set it up right. Not absolutely, but we've got a really good chance to set it up right. So now we're ready to plug in the values into our calculator. All right, we don't have to do anything to this side. We've isolated V2 all by itself. That's all we have over there. Huh?
Why are you moving liters?
Why are you leaving liters? We're not moving it over. I'm showing you liters, the unit, matches the dimension of measurement here. I'm not moving it anywhere. Okay, please don't misunderstand when I do this that I'm saying we're moving it over. Okay, is everybody clear with that?
No.
You're not clear with that?
Oh, no. Go ahead. It's fine.
But do you understand I'm not moving it over? I'm just showing it belongs.
Go ahead.
All right. So what we're going to do to solve this is we're going to take this 288.2 and multiply it by 4.75. Okay. So 288.2 and multiply it by 4.75. And then we're going to hit our enter button. Now as a separate operation, then we're going to divide by what's in the bottom. Divided by 308.2 and hit enter, and that's the answer we're going to look for there. Okay? Yes, ma'am. Robert Jackson, yeah, Reese. Okay. All right. So our full answer then is 4.44175.8598. Or yours may have fewer digits. That's okay. All right. And if we look at the equation, what we have left on the other side of the equation is V2, and what we have left for units is liters. And now we're going to do the same kind of rounding off we've been practicing since the first unit, actually, where we first learned about rounding off. And we have 4 digits in this number, 4 digits in this number, and 4 digits in this number. These are all measured numbers, and this number we're not going to worry about because it's a placekeeper.
That's 3.
I'm sorry, 3 here, you're right. Okay? So, because this number right here is not going to be important in figuring out significant digits, this one has the least digits. So we're going to use the same number of digits in our answer. 1, 2, 3 are our significant digits. Underline everything else. Use a rounding arrow. And our final answer is 4.44 liters equals V2. Okay? That's how you solve the problem. All right, so here are our steps again. Let me remind you of your problem-solving steps. And we didn't talk about in the very beginning you have to interpret the problem. But that's what you're doing when you're making this list. Are you listening?
Yes, sir.
We're interpreting the problem to find our list of knowns and unknowns. And then the first step was to make a list of knowns and unknowns. The first step was to make a list of unknowns, a list of knowns and unknowns. The second step was to go to your test references and find the equation that best fits that list of knowns and unknowns and write that equation down. Okay? And we're then going to substitute in the known values in the equation. That's what we did in between my fingers here. Okay? We substitute in the known values. Now the thing that you have to remember with gas laws is temperatures have to be in K. So that's kind of an intermediate step in there. Once you make your list of knowns and unknowns, go ahead and change your temperatures to Kelvin if they have to be. All right, so we've substituted our knowns and unknowns. Now we're going to isolate the unknown by setting up the equation in a way that will do that. So in this case, we multiply by these two numbers here on both sides. Remember, what you do to one side, you have to do to the other. Then you cancel, and then you do the math we've learned to do for, a couple months now. Yeah.
How do you know when it needs to be converted to Celsius?
If the problem asks you to convert it to Celsius, you do. Okay? Any other time you don't have to convert to Celsius. Now, you always have to convert to Kelvin to solve a gas law problem. But you don't have to convert it back to Celsius unless the problem tells you you have to.